Yeah, thank you everyone for joining me here today. We've had a bunch of talks about AI, so let's try to get back on topic today. I'm going to be talking about good old Kubernetes and platform engineering. So, my name is Jennings. I am a research scientist and software developer at the Boston Children's Hospital. We are the world's largest pediatric research enterprise, and we receive the most grant funding from the National Institutes of Health here in the US than any other institution. We're also a Harvard Medical School affiliated teaching hospital. Within Children's, I specifically work for an academic research lab known as the FNNDSC, and our lab focuses on developing advanced neural information processing systems. You see? Neural information processing systems, right? You know, made out of neurons, the real ones, you know, axons and stuff. I promise you, AI will not be the big focus of this talk. So, at Children's, we are researching experimental methods for doing in utero magnetic resonance imaging. And what that means is we take MRIs of pregnant mothers and we look at their fetus's anatomy. Imagine for a moment how difficult it is to tell a kid to sit still for the camera. Fetal MRI is kind of like that, but even worse. It's not exactly possible to tell a fetus to hold still for a moment. Although this is very challenging, we figured out ways to take repeated scans and stitch together into one high-quality image, and we do this using machine learning. Of course, we need a place to run all of these machine learning algorithms. And today I'm going to be sharing the infrastructure we've developed to help facilitate this advanced image analysis for clinical purposes. It's by no surprise that we actually have this technology. If you just do a simple, very quick online search, you can see that medical research, machine learning, has just blown up. In fact, the growth curve looks logistic. It's maybe flattening out in the recent years, but the point is we have a lot of this technology. As we're doing more and more research, we are acquiring new knowledge, and that new knowledge leads to new research questions and more research, of course. But we have one remaining unsolved problem, which is how can we take the products of research and actually deliver value? In our case, how can we improve patient care? So it's no longer a question about whether or not we have the technology, because the year is 2024. Technology is awesome, AI is awesome, Kubernetes is awesome, but even though we have the technology, how are we using it to improve lives? My lab is more than just a research center. We have 3 divisions. The maternal care center is where we have clinicians working with real patients every day. We have a developmental science center where we have a team of over 80 faculty, students, postdocs, and research staff like myself doing biomedical research. And then we also have the advanced computing group, which is also a part, or something that I'm a part of. And we develop software and maintain infrastructure that supports both the clinical and research activities of our center. This is how all of our work is done traditionally, and it's pretty complicated. It requires a specialized set of skills. First, you're gonna want to SSH into the cluster and presumably use something like tmux or zelij to preserve your session. After that, you need to transfer your data from the MRI scanner to the file system, and then you request some resources from the cluster. This can be done any number of ways, depending on which institution you're at. At Boston Children's, we use Slurm. Finally, you want to run your analysis program. I assume you'll want to use some kind of container runtime like Podman, Docker, or Aptainer just to make installation easier, but that stacks on yet another layer of complexity. Now you have your analysis results. What do? Well, you need to copy it off the cluster once more and run some visualization software. Good luck with that, because typically visualization software is quite challenging with the outdated X11 dependencies of them. Introducing the CRIS project. CRIS stands for the CRIS Research Integration Service, and it's what my team and I have been working on for the past couple of years. This is what the user interface looks like. And so what we can do is we can take those advanced image analysis software, and then we can run them in pipelines as Kubernetes jobs. And then we present this user interface to make it super easy to create these jobs, manage your data, and even visualize the results. Here is an alternate user interface that we have specialized for the purpose of running a fetal brain MRI reconstruction pipeline. And so our goal is to present a minimal, simple user interface for clinicians with no technical experience to be able to leverage Kubernetes and cloud computing to execute these very advanced algorithms. So on the left, you see the actual outputs. And then on the right, you see what the inputs are. The inputs are fetal brain MRI scans. And then what this algorithm is going to do is it's going to try to clean up the scan, mask out the brain, and present this picture of the brain, which is so much easier to use for downstream analysis. How this all works is we have an open science and hybrid cloud architecture. First, all of our actual analytics software that we run is stored in some kind of public software repository. Specifically, we're going to be talking about container registries because everything is containerized. And we distribute the software to not just our own hospital, but other hospitals as well. Then, we can use this software on internal clusters, which is important for protecting protected health information, or PHI. But we also have the option of sending some of these Kubernetes jobs off-site to public clouds where we have so much more compute. Some of the strengths of our system is that because we have designed everything around container images, this really facilitates and it makes it easier for us to uphold rigorous scientific standards, such as reproducibility. And it also helps us do this research integration much more easily. Now, I've talked for a long time, and hopefully I've made this project sound really cool. I'm actually going to dial it down a little bit. This little sad picture here, this is Boston Children's Hospital's first production Kubernetes cluster. This is my love child. I created it. I use Kubespray and Ansible to install kubelet on every single one of these machines. As humble as it may look, we have run production pipelines on this Kubernetes cluster, and it has served us very well. Don't worry, we are trying to get another cluster up that's running in an actual data center on server racks. But the point is, we're able to achieve all of this for very low cost on commodity hardware. And even though we have limited compute resources on this tiny little cluster, I guess you could call it, we're able to send the jobs to public clouds and use a hybrid architecture to handle the demand of compute. First, I'll talk a little bit about what it actually looks like. You can easily create what we call Crisp plugins using Python or any kind of programming language. If you are using Python, you can see we import the standard libraries argparse, and it will automatically understand what you're trying to do. Regardless of whether you're using Python or Rust or whatever your favorite programming language is, to run something on Crisp is super easy. It just needs to conform to this one simple spec, which is it needs a name for the command to run, of course. And then it has two positional parameters, a directory for input files, and then a directory where to write the outputs. Once you've packaged an analysis software according to that simple spec, what we can do is we can automate the execution of your software and analysis pipelines using cloud-native technologies. First, we receive images from the hospital's hardware, such as MRI scanners, CT, X-ray, over a legacy protocol known as DICOM. The DICOM goes into our Kubernetes cluster, and then from there on out, we're using purely cloud-native technologies, such as Knative serving and OpenShift serverless platform to handle webhooks and events. But once again, if we need more compute resources, we can send our data to other Kubernetes clusters, maybe in the public cloud. We can even bridge our Kubernetes cluster to the existing traditional HPC environment, where we send data over the NFS protocol, and we actually execute the jobs over SSH. So putting it all together, this is what a typical workflow is going to look like. We can pick and choose the right compute resource depending on what the computational needs are. So the typical first step is we want to anonymize our data and strip it of any protected health information. Because we have protected health information, this has to run on-prem and ideally somewhere close to where the data originates from. And so, of course, we're going to choose our on-prem cluster for that. The next steps of the pipeline get more advanced, such as an image denoising algorithm. That is going to do some pre-processing on our data, and we're going to use Chris to send this compute job to an external elastic public cloud where we can leverage faster CPUs and more CPUs. Once the image has been pre-processed, we do another step, which is a neural net inference. Neural net inferences need GPUs, and we choose to do this on internal resources, whether it be our on-prem cluster or the private high-performance computing center. And the reason we do this is to save on costs. Cloud GPUs can cost a lot of money, but if we run this internally, it's all free. And the last step is to generate a simple PDF report that the clinicians can see, read, and use. This is a very lightweight task, and so we can choose to run it close to where the compute is, close to where the data is on-prem. To actually distribute the backend for Chris, we have packaged it as a Helm chart. And so our main hospital, Boston Children's, is of course in Boston, US. And we use the same Helm chart to deploy our compute resources on our internal cluster, on the public clouds we use. But we also use this method to share our technology with our collaborators. And so we actually have collaborators in Toronto and London, which has a funny acronym. It's the BLT collaboration. Even beyond that, we are collaborating with the Cure Hospital in Uganda, and they are using Chris to perform neuroimaging analysis as well. So thank you, everyone, for attending my talk. I hope you guys learned something. This QR code on the left is going to take you to the sketch.com page where you can leave feedback. I'd like to thank my supervisors, Rudolph, who is the technical director, and Ellen, who leads our center. Those 4 pictures are my teammates, Xiao, Gideon, Sandeep, and Jorge. Lastly, if you want to join our Matrix channel just to talk and hang out, there's a QR code on the right. Thank you, everyone. Questions? Yeah.
Thanks for your talk. So we're in a similar boat at the University of Utah, trying to build a Kubernetes platform. Do you have any? Is there anything you can say about like how you started this journey? Like you showed a picture of your first Kubernetes cluster, and it's very bespoke. Were you able, like, how are you able to turn that into something that's running in production, with all the, red tape and all involved? Did you have a lot of support, like, going into this project, or, like, how did you navigate that?
Yeah, that's a really good question, actually. So the question was, we pioneered the usage of Kubernetes at our institution. How did we work around that? Because it's a hospital. There's a lot of red tape. How do we pass the audits? And initially, we wanted to collaborate with the research computing department of Boston Children's and also Boston Children's ITS. But you're right, there is a lot of red tape, which is why we did this all literally on the floor on retired workstations, commodity hardware. And going into the data center would have been a lot more red tape. This is one reason why this is how we started. And for the most part, our Kubernetes cluster wasn't really audited or approved by the hospital. We keep everything in the intranet. We're careful about how we deal with PHI. So from the hospital's perspective, we're just a bunch of nerdy software developers playing around with computers on the floor. But now that we're actually getting bigger, now that clinical workflows are being run on our Kubernetes cluster, the hospital has paid more attention to us, and they realize that we are creating value for the hospital. And so now they are more supportive of us, helping us get server racks in data centers and helping us with funding as well.
So my question is, what do you think the benefit of having it be a hybrid cluster doing things on-prem and in the cloud, as opposed to maybe doing something strictly on-prem or strictly in the cloud? And does that have something to do with the PHI information?
Yeah, so the question was about what are the advantages of a hybrid architecture? PHI is definitely a very important part of it. So no matter what, we have to keep some of our compute and all of our data on-prem. So the question is, why do we go to the cloud? The answer is it can help save us some costs. I think it was a really hot topic this year at KubeCon about how can we save costs, how can we optimize our cloud computing usage, because the bills can rack up very quickly. And so the reason why is because scaling up internally is very expensive. Using internal resources is cheap, but scaling is expensive. So any kind of like overflow in compute demand is the situation where we want to send things to the public cloud. And we have to be careful about that. All of the like PHI processing algorithms are for the most part lightweight. Usually we're just trying to strip the PHI. Image processing algorithms can be a lot heavier, and any kind of CPU-bound image processing algorithm is a good candidate for something to run on the public cloud instead of on on-prem resources.
Thank you.
Thanks for the talk. It was awesome. I just had one question about your Python framework that you wrote, which who are your users? Like, who is using that framework to run jobs? Is that like you and your team, or is it going to be like multiple teams? Like, who is that for?
Yeah, the question is, who are the users of this Python framework? I guess you could call it an SDK or framework, but there is very, very little going on here. I wanted to quickly skip over it, but I guess I can talk about it a little more in detail. So you can see that we're importing argparse from the standard library of Python, and then we import this Chris plugin decorator from our custom SDK. You just slap that decorator on top of a main function, and then everything else is just vanilla Python. There's very little effort you need to put in to adapt a existing solution to run on Chris. About who uses it, yes, our lab, of course, is the primary consumer of our own dog food. The software that is developed at the lab, FNNDSC, is typically wrapped into these Chris plugins so that we can run them all on Chris. Other open source image analysis software that we need to use, we also wrap in this Chris plugin. And some of our collaborators are working on other image analysis software, such as the BLT collaboration, Boston, Toronto, London. They would be writing Chris plugins using this template as well.
Awesome, thanks. And also just wanted to give a shout out to the name. I don't know, it's also my name.
Thanks. I got one more question. Regarding the traditional HPC, you had on your data flow slide, you showed there's still like a traditional HPC component. Yeah, this one. So can you comment on how the new Kubernetes Chris framework relates to the traditional HPC? Was there like any kind of migration process involved, or is the Chris just kind of new stuff that complements what's already there?
Yeah, so the question is about how the Chris project interacts with traditional HPC. we started developing the Chris project on Docker Compose, and then we moved over to deploying on Kubernetes, of course. So the Chris backend and the Chris architecture is pretty cloud native, you could call it. But we do need to interact with the existing HPC at Boston Children's Hospital because it's just a great resource for us to use. The problem is there's no kubelet running on HPC. We can run containers using a container runtime called apptainer. And we can schedule jobs and request resources using what's known as the Slurm scheduler. And what we did was we developed a shim so that we can run Kubernetes jobs on Slurm using apptainer. And so if you want to run a job and you choose to run it on a Kubernetes cluster, it's pretty simple to do. If you choose to run a job and you choose to run it on the high performance computing cluster, what we need to do is we need to translate that Kubernetes job into a SSH command. And that SSH command is going to look something like srun --mem 8gb apptainer exec OCI image name command.
Is the code for that shim available?
Yes, everything is MIT licensed and open source. Let's see. Let's drag this over. Let's maximize. Said maximize. OK, well, it's not going to maximize. GitHub. Sorry, I can't even see my screen. Yeah, so this is a somewhat poorly named microservice, pman, process manager. And what pman does is it provides a unified interface for running Kubernetes jobs. And it can execute things on Kubernetes, of course, OpenShift, Podman, Docker, and Slurm. If you go to chrisproject.org, that's our website. I will try again to maximize it. Please, please, please. Oh, thank you. Am I clicking on architecture? Getting started?
There you go.
There we go. Yeah. So this is a technical architecture diagram. Not everything is necessary to understand, but the point is we start off from the user interface. The user is going to request to run a job, and it will end up going through our architecture, and it'll hit some kind of compute cluster resource. And it can be either Kubernetes, or it can be a single machine running Docker or Podman, or it can be a traditional high-performance computing cluster, such as Slurm. I think it wouldn't be too difficult to add support for other HPC schedulers as well. Of those, I'm aware of like Oracle, SunGrid Engine. OK, that's all I can name.
All right. Thank you very much.
Hi, quick question. Could you talk or go a little bit more into, on one of your slides, you said like, how has this helped your, the patients? So like, what are some of the tangible benefits that you've seen from implementing this hybrid Kubernetes architecture to do your machine learning based imaging process?
Yeah. So the question was, how exactly does the CRISP project benefit patients? How do we improve patient care? I'm glad you asked that because it's very much more focused on the medicine and biology side of things rather than the infrastructure. Now that you understand how the infrastructure works, what we do is, give me a moment. This page. This is what I've been working on most recently. As I said, it's a fetal brain MRI reconstruction pipeline. At the Maternal Fetal Care Center, it's very typical for pregnant mothers to get an ultrasound of their child. But let's say something unusual is found in the ultrasound, and we need a higher resolution picture of the brain to see what's truly going on. And so they're going to do a fetal brain MRI scan. This is a experimental technology that is quite rare in the world. Boston Children's is doing it. Off the top of my head, I know like 4 other hospitals in the world that are working on fetal brain MRI. But the point is, this is on the cutting edge. And the techniques that we use to analyze fetal brain images are mostly computational. And we need to be able to run this somehow. The software developers who have created these algorithms are typically interested in proving that it works, publishing a paper, and then moving on to their next paper. What we do is we take the open source software and the AI models that they've trained, and we put it on Kubernetes, and we put that in front of physicians. So looking at the picture on the right, that's a fetal brain MRI scan. What we do is we take multiple scans and then we stitch them together to create a higher resolution and more clear picture. From the reconstructed image, which you see on the left, it is easier for a clinician to be able to see what's going on. You can use this web user interface to measure certain parts of the brain. For example, you can try to measure the ventricles, which are components of cerebral spinal fluid. And then let's say the size of the ventricles is off. You might suspect that the patient has a certain condition, maybe fetal ventriculomegaly. And then from there, you can make a recommendation to the patient of how do we move forward with treating this condition, what to expect for the family. Or we can even take this image and do some further downstream processing. Some examples of that might be, go back to the first slide. Yep. Nope. Yeah, we can run more machine learning to do segmentation on the brain. And then once we get that segmentation and we know what's what, we can do what's known as surface extraction to reconstruct the brain from a 3-dimensional voxel-based image to a polygonal mesh. And using that polygonal mesh, we can automatically measure the thickness of both cortical and subcortical structures of the brain.
Cool, thank you.
Mm-hmm. All right, once again, I'd like to thank everyone. I truly appreciate everyone for being here. Yeah.